Welcome to this edition of Shadow the Scientist. My name is Jamaica Marshall, and I am pleased to serve as the coordinator for the Shadow the Scientist initiative. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. In this session, we have the privilege of shadowing the crew of Expedition 402 on board the JOIDES Resolution research vessel. The JOIDES Resolution, JR, is a seagoing research vessel that drills core samples and collects measurements from under the ocean floor, providing scientists with a glimpse into Earth's development. JOIDES is an acronym for the Joint Oceanographic Institutions for Deep Earth Sampling, which represents the original partnership of universities that sought to explore the geology beneath the ocean floor. Today, the ship is used by scientists at hundreds of universities around the world. Data from the JR's ocean drilling offer a scientific means of understanding climate and environmental change throughout a significant part of our planet's history, a research subject often termed Earth's paleoclimate. The JR's core samples are the smoking gun in evaluating many historical events related to paleoclimate, changes in the solid Earth's core, and more, like the extinction of the dinosaurs and plate tectonics. Our guide for this session is Onboard Outreach Officer Tessa Pezzotto. Welcome, Tessa.
Hello, hi, it's nice to see you all. I'm excited to be here. Thank you for that introduction, that was wonderful. The JOIDES Resolution is a fantastic ship. We frequently like to say it's a legendary research vessel, and I'm really happy to be able to share it with you all. We are actually in the Terranean Sea off the coast of Naples. So let me see if I can show a photo of where we are just on a map, just to make it easier. And it is pitch black outside because it is nighttime for me. So I unfortunately cannot show you the vast Terranean Sea, but we can start with this map and then I'll show you a photo of what it looks like during the day. So we started out in Naples on February 14th and then sailed into the Terranean Sea, and it was only actually 4 hours transit. So we're actually quite close to land at any given moment. And we are having drilling locations near the coast of Naples in the Campania Terrace over here. And then we even went all the way over here to the Conaglia Terrace near Sardinia Island. And we've also stayed a lot in this area where you see the black arrow. That black arrow is pointing to the deepest part of the Terranean, which is called the Vavilov Basin. And it's a real big interest to the scientists on the ship right now, because it also is a location where we have collected mantle rocks. And mantle rocks are extremely valuable to our scientists because we can understand and study how the mantle actually changes when it gets exposed to seawater, and also how it got exposed in the area. To give you an idea, the mantle typically is 30 kilometers below the continental crust. And actually here, it's only 300 meters below sediment. So it's actually quite easy to access, and it's quite crazy to access because when the part of the Terranean Sea 15 million years ago was not actually a sea itself, it was just a bunch of different islands together. Specifically, this part of Italy was next to these two islands here. And about 15 million years ago, the microplate tectonic got pushed or pulled in this direction where it fit this part of Italy right next to the rest of this mountain range, which is called the Apennine mountain range. And by moving all the way eastward, it opened up the sea, but it opened up the sea quite fast geologically because it happened in less than 15 million years. So a lot of the sea floor got stretched and cracked, basically. And so that's where the mantle was able to come up in the middle of the Vavilov Basin and potentially start getting altered by the seawater. I like to think of it like when ships are in the middle of the ocean, seawater is quite corrosive. It causes rust, it can cause erosion to metals. can do the same thing to rocks. So the scientists here want to look at what's happening to the mantle rock as it gets exposed to seawater, because it's not every day you get to go look at mantle rock. The other part is to look at the continental ocean transition on the coastlines of Italy and the islands to understand what is the middle part between when it's not oceanic crust, but it's not continental crust. What does that rock look like, and what is it made up of when it's in that transition zone? So they want to understand that. What that all adds up to is the big question: how did the Terranean Sea open and what changed? That's the main question they want to answer, and it goes with the mantle rocks and continental ocean transition areas. That's the background. But the way we do that is we have to drill into the ocean floor to get to those rocks. So I'm going to take you outside to show you where the drilling floor is. So like I said, it is pitch black right now for us. So this is what it looks like during the day. A beautiful expanse of Terranean Sea with a lovely blue sky. However, when it is nighttime, we are the only light source out here, and we are actually underway to our next location. So the boat is darker than it usually is. So here you go. So pretty dark. I don't have much of the Terranean Sea to show you right now. And like I said, when we are traveling to another location, there are no lights lit on the boat. However, when we are drilling, we light up this boat like it's a city, mainly because we need to make sure that we can see what's happening and that ships can see us outside of the radar that the ship uses to indicate our location to other ships. So you can kind of see we're moving a little bit. We're the ocean creating its ruffle. But what makes us a really special ship is our derrick, and you can kind of see it in my picture. It's not lit up very well, so let me show an image here. And our derrick is so in other languages, I find it interesting. In other languages, it's called the Tower of Perforation. In English, we use the word derrick, and I learned that it's actually a Roman word to indicate a tower of sort of like drilling, holding of structures. But our derrick is this middle tower here, and it is what allows us to do deep sea drilling. It is about 45 meters above the ship, and when you account for the height of the ship, it's about 60 meters tall total. And the ship itself is about 145 meters long. We're about 460 feet. And sorry, I didn't say the feet measurement for the tower, for the derrick. It's about 200 feet tall, 220. So this really makes us a special ship because not all ships have a derrick on it. And what makes it really cool is that we actually drill straight through the ship. So we have the rig floor over here, and I'll get closer in just a moment. But right under my moon pool sits. My moon pool is a hole in the ship. So instead of having the pipe move around the ship to get to the bottom of the sea floor, I have a hole. And so this is a picture of the moon pool when the door that covers the hole opens up. So this is when we only open up the moon pool when we're sending down what we call a VIT camera, where we need to see where we're going if we're going to re-enter an already existing borehole. We usually leave the doors closed because we don't need them open to send the pipe through them. There's a little guide horn, little specific area right here on the moon pool that allows the doors to be closed and the pipe to go through. And so when we are drilling, can go upwards of like 3-4 miles deep, sometimes even 6 miles deep. And this is what it looks like. We use our most flexible drill pipe in the top of the water column and our most sturdiest, strongest, thickest walled drill pipe in the sea floor. We need the flexible drill pipe because our ship will move back and forth with the current. And so we need this pipe to be able to move this way and that way with the ship. But we want this pipe to not move with us. So it stays more sturdy and more like in its place and stabilized. So that is just the image of showing you how the ship sits on the sea floor when we were drilling. And then we don't have a pipe deployed right now. but you can kind of see some of our most sturdiest pipes down below. These are the ones that sit in the sea floor. So we have these that are a little bit more orange colored, these that are a little bit more steel colored. They are the ones that we call the bottom hole assembly. They're the ones that go in the borehole and that need to like kind of stick with the drill bit and turn with the drill bit completely without going wobbly with the ship. This steel one is actually non-magnetic material, so we try to reduce the drilling imprint that the drilling can have on our core samples because we are also measuring magnetic signatures of rocks. So we try to have at least one part of the bottom hole assembly a non-magnetic material when it's going in circles. So let me get closer to the drill floor. So right now I'm on the bridge deck, which means almost our topmost deck. So I'm going to be looking down onto the rig floor. And we partner with an offshore drilling company called CM Offshore. And these are my team, the CM team. They are the experts of drilling. No one besides them is allowed on the rig floor without their permission because they know exactly how each of these equipment work and the safety that goes along with that equipment. So we trust them to do everything we need. And we're very thankful because they are able to get the cores that we need to study. The CM Offshore team also consists of our sailing team, so our captain and our first mate, our mechanics, and our electricians. So they actually operate the whole vessel. They make sure the ship is actually livable. And then we partner with Entier, which is our catering crew, which I can talk about a little later. So they are currently washing it because we just finished all our drilling operations. So they're getting rid of like the grease that falls on the floor and also all the mud and rocks that kind of happen as we take out a core barrel from the pipe. But the pipe goes through this little hole right here. It looks red right now, but it usually is open and the pipe goes straight down there. And you can kind of see there's a pipe actually sitting right here. So this red structure is called the pipe stabber. It'll actually bring the pipe outward, and this yellow structure right here called the top drive, they will hook it up with the pipe and then it'll go all the way up the top of the derrick, all the way to the top to make the pipe vertical. So we store our pipes horizontal and then the top drive will bring it up vertically to go down to the sea floor. Our pipes sit in 30-meter stands or sections. So I want you to think of us building the drill string as making a really long straw. If you ever like, I don't know, I've done this with milkshakes. So when you try to make like one straw with another straw and another straw, and you try to drink that milkshake through that long straw, we do that with the pipes. So we use this machine right here called the roughneck to like twist the pipes together and really tighten that twist so that when we drill, they don't undo themselves. And we attach those 30-meter sections to each other until we can get down to the ocean floor and through the ocean floor. So I calculated it one time. So 30 meters each stand, for us to get to a 3,500 meter depth is about 116 pipe stands all together. And so this is what they do. They connect one, drop down, connect one, drop down, connect one, drop down. So it's just 12 hours of them just building the drill pipe. These metal barrels that you see right here, these are actually what the core is actually collected in. So the drill pipe stays deployed the whole time. These core barrels are the ones that go down with the when we're ready to start coring. As the drill bit turns, the core barrel will collect the core. Once it's full at about 9.5 meters, we'll send a hook down on a string through the drill string, pick up the core barrel and bring it back up so that we never have to bring the drill pipe completely all the way up. We just open the drill pipe when we're ready to collect core. And I'll take you down to the core deck to show you how we prepare the core once it's taken out of the core barrel. And then I just wanted to check, Jamika, are we taking questions now or later?
We can do questions at the very end.
Okay, cool. So now I'm on the main deck, which is aligned with the rig floor. And so what they'll do is they'll rest the core barrel on this little yellow stand horizontally. So it's 9.5 meters long, about 30 feet almost. And we'll just pull out the core liner, which are these plastic tubes right above me. And we actually get these custom made. We actually call into a manufacturer and like, hey, can we get more of this core liner with this dimension? We can't go to IKEA to buy these core liners, so we get them custom made and shipped to us. So the core liner sits in the core barrel and we bring it out on our shoulders of the marine technicians and bring it out to these tables out here to rest the tube on. And just to give you an image of what that looks like, this is an example of when we have a core out on these tables. And it is just this long tube of sediment or hard rock. And what the marine technicians have to do, so the scientists haven't even come out yet. We've had the CM team get the core and we've had the marine technicians to prepare the core. And they will basically cut the 30 feet long tube of sediment or hard rock into about 5 feet long tubes, and then assign one end of the tube with a blue cap and another end of the tube with a gray cap. One indicates the top half of the tube and the other end indicates the bottom half. This helps with orientation. So I know which part of the section is closest to the top of the seafloor and which part of the section is closest to the bottom of the seafloor. Another cool thing is this ship is incredibly innovative with how they prepare these materials. This core cutter was designed by a marine technician. So they basically they used a 3D printer to design it to wrap around the core and then put a razor blade just in this little section. So all they have to do is just swing it around the core liner instead of using a knife to hack at the core. And they also sent it to a manufacturer to make it in metal, and now we have a ton of them ready to go. So it's really awesome how innovative just the marine technicians and the engineers are on the ship, beyond just the scientists too. And then what I wanted to do also is I wanted to indicate a close up to our drill bits. So our drill bits are designed for different formations of the seafloor, meaning this drill bit would only be used for soft or hard sediment, while this drill bit would be used for hard rock. They are designed differently. So a soft sediment drill bit actually has a wider diameter in the middle to fit the core barrel. So you can see here, we have our core liner that goes in the middle. The core liner is inside the core barrel. The drill bit's attached to the drill pipe. So when we're doing soft sediment coring, this actually, with the core barrel, so inside the metal tube, will actually shoot out into the sediment to punch through the sediment instead of drilling the sediment. That preserves the layering of the sediment much better for us. So we only ever use the rotary cones on the soft sediment when we start getting to harder sediment that has been compacted so much, it's almost like a rock, but it's not fully a rock. The hard rock drill bit, only ever used on hard rock, and they have different sizes based on the teeth that sit on these rotary cones. The more pointy they are, the softer the rock. The more flatter they are, the harder the rock. And these will actually turn based on compression. So we will use a drill bit, and the weight of the drill string actually pushes down so much on the drill bit that it'll make these cones turn. And then they will fracture the rock in the borehole as the whole drill string is turning and putting weight. So we actually use weight and compression to really make our borehole. So we don't have a motor in these cones. We just use weight and pressure. And that's how we create our borehole. And which is pretty awesome. And then, so those are our drill bits. That's an example. They're upside down right now. They actually go rotary cone face down into the hole. It's just easier to rest them like this. But so far, we've went over the drill floor or the rig floor and how the core comes out to the technicians. Once it's cut into pieces, we go into the lab, our core lab. And every door on this ship on the outside is weather tight. So it has this giant doorknob here that we always have to spin and tighten so that we make sure that no weather comes into the lab. But this is our core lab. And the first part of our core lab is where we call the physical properties part of the lab, where we basically take the whole round of a core, which looks kind of like this, just a whole cylinder of sediment. And we put them through these different machines to take measurements as close to when they came out of the hole as possible. I like to think of it as when we go to a bakery, we want to get the freshest bread. Here, we're trying to get the freshest analysis of the cores. So we have different machines like natural gamma radiation. We have thermal conductivity to see how much temperature moves through the rock or sediment. And then we also have this machine here that takes density measurements, magnetic susceptibility measurements, and then also we called a P-wave velocity. We actually shoot sound through the rock or sediment to see how fast that sound travels through it. And I just learned today, which is crazy, and I feel so happy I learned it. This measurement actually helps us verify if our seismic readings are correct. And if our seismic readings are correct, great, we can keep using them. But if they're different, we can use this data to ground truth it, to recalibrate the seismic readings of the rocks. So it's really great because we're doing validation of data consistently as much as we are getting new data. And then this is our shelf of acclimation. Right now, we don't have that many cores on it because we actually cut them all. But when they get cut, they get turned into half sections. And they technically, when they're a whole round, they sit here to get acclimated because we just took them out of 3,000 meter depths where it could be cold, it could be hot, but they have a certain temperature and then they have a certain amount of pressure on them from all that water. We bring them up to our atmosphere and our temperature, so we leave them here to acclimate. And we have a cardboard here because sometimes they start to leak a little bit because it's at a different pressure. But I have my physical property scientist here, Brandon, who works in this part of the lab, and he's going to tell us about the X-ray machine, which is brand new and it's really cool. So I'll let him talk about it.
Sure. Hey, everyone. My name is Brandon. I'm on the physical properties team here. So one of my jobs is to basically run all the instruments of the cores after we get them and look at various physical properties that we have that can help out understanding the various descriptions that we have of the lithology and mineralogy, and then we can relate those to the bigger scale for the geophysical information that we have underground, and even scale that up to large scale seismic imaging across the basin. So taking all the information that we're getting from the rocks that we recover and trying to extrapolate that to, for our science program. So one of the tools that we use is this X-ray imaging machine. We've been using this to image both soft sedimentary formations as well as hard rocks. So what this is, it's very similar to a medical X-ray imaging. For instance, if you had an injury or broke a bone and you go into the doctor's office, and so they're able to actually see inside and see what's wrong with you or your bones. And so we're doing the same thing here for the rocks, where we have an X-ray emission source and it's traveling through our section half cores and then being detected on the other side, and it actually slides along across the length of the core. So we're actually taking these X-ray scans, and this is helping us image the internal structure. So for sedimentary rocks, we can look at different bedding features such as stratification. We can also see areas of fractures, although it doesn't show up as well typically on sedimentary rocks, but also areas of drilling disturbance that is caused by basically artificial damage from the drilling process, which is really helpful for the people that are describing the rocks to understand what's real and what's artificial, so we don't accidentally interpret something as geologic significance. And then for hard rocks, we've been getting really good images of the various fracture and vein networks in the mantle rocks that we've been getting, because they're filled in with carbonate, magnesite, and calcite, and they're showing up really well and giving us information about the stress field and the fracturing and how fluids are moving through those rocks. So should I put one in?
Yeah, sure.
Okay. So I can show you an example here machine. So here we have some split cores. This is part of the Messinian interval that we just recovered. So we have some more hemipelagic nanofossil ooze and mud, but then we also have areas where we've recovered some evaporites, which is really exciting. So here are some gypsum, and we have other areas where we think we have halite. So this will help us right now you can only see what's going on at the top, but you can imagine that some of these little blotches are buried down in there. And so the X-ray imaging will actually allow us to see if we have, for instance, different variations in density that are somehow buried in there. So we load the core, we scan it so that we get our ID all set up in the system, push our core inside, up the system so no radiation is getting outside, so we're all nice and safe. And we can go ahead and scan that. We have to make sure that we carefully adjust the settings for the different type of rocks and imaging that we're interested in, because what this is essentially telling us is the density of the material. So the X-rays are passing through. Denser material is going to absorb more of that. So less of those X-rays will get to the other side of the detector. If it's less dense, then it'll pass right through it. But hard rocks, for instance, the mantle rocks that we're getting are much higher density than all the sediments that we're recovering. So we have to make sure that we optimize all our instrument equipment to best illuminate the features that we want to see for the different density properties that we're getting in the various amount of rocks that we have. So that was just an example of going through scanning. I'm not sure if you saw here is the system. It had already gone through and scanned. Now it's working its way back. We can do this at different angles. So the core is actually sitting inside of here, and the scanning system went along. And then, for instance, we can go over here and look at the different processed images that I'll get. So we actually collect the X-ray image all the way down through the core. And so the lighter areas are the less dense material, and the darker areas are the more dense material. So, for instance, you can see the core liner, right? That's the plastic. I think it's plastic. What's on the outside? Very low density material. And then you can see these darker patches are those evaporites that I just showed you before, where you can see that we have these darker blotches to them. There are some other features that we can see. We get this classic fractures across, and those are actually from the drilling process. So these are not real features that were there in the subsurface. They're features that we created from extracting the rock and bring it back on board. So again, this process can help us look at those features that we don't want to interpret as having geologic significance. So
cool. Thank you, Brandon.
Yeah, you're welcome. Thanks.
They're applauding for you.
Oh.
So that's our physical properties. And so basically it just gives us those characteristics that we want to see. But when we're, this is our splitting room. So when we're done with the whole round, like you saw with Brandon, we put a section half into the X-ray. We do have a splitting room where it has multiple different saws in there to cut the whole round in half. But when they get cut in half, we have two halves. One that's called the working half, where we can basically take as many samples as we want as possible. Philippe is looking at over his shoulder. He's like, don't judge me on how many samples these takes. And then we have our archive half, who is you do not take anything from, we just purely describe. So anything you can see visually is what we are taking into account there. But let me show you what I mean by taking samples. Each of the scientists have their own little sticker here. And so when they come over here to the table, they'll put a sticker down at the interval or the layer that they think they want to take a sample from. And for instance, MAD means moisture and density. So this is a specific sample that, for example, Philomena will be taking. You do moisture and density. But then there's like carb, there's distribution, there's paleomag. So there's different stickers to indicate what sample needs to be taken for what test. So this table gets covered in stickers. And essentially as a working half, these samples are destructive. We can't put the sample back most of the time. So this starts to become like a pockmarked half, like where there's empty spaces. And that's okay. That's okay, because we need to do those analyses now to understand what we're seeing so that when we describe them over here on the archive half, we don't have to take anything from the archive half. They just get preserved and sent to our repository in Texas, Bremen, in Germany, and Japan. So our repository basically is a giant refrigerated library that looks like this. So just stacks of cores. The black cap cores are the ones that are working halves. So the ones that might have empty spaces because of how many samples were taken. But the red caps are the archive halves from every expedition since 1960. So you can still take cores from expeditions 20 years ago if you want and do science on them. And I actually have scientists on board here that are using expedition data from 20 or 10 years ago. They're still using it for their PhD, for their postdoc research, or even their career research. So it's incredibly important that we preserve these cores for future scientists as they start to understand and uncover the Earth's secrets. Let me stop sharing here. I'll take you over to our sedimentologist. So Lorna, for example, works at University of Texas at Austin. Yes. So she is our sedimentologist on board. So she's at our archive table. But do you want to tell them what you do when you look at these samples?
Yeah, sure. So when we get it onto the archive table, like Tessa was saying, we want to preserve the archive as it is. So one of the first things we do is take high resolution photographs of the archive art on this machine here, which is called the Shill. And what this does is it's a camera that's on a track and it just moves along and images the core. So that way in 20 years time, if someone wants to see what the core looked like, they can. And then we bring it back in and we describe it, and we describe things such as color using this fancy book here. And then we also describe things such as grain size, any class that we might see, any macrofossils, but also drilling disturbance. So when the cores are drilled, it does create some artifacts that are then preserved in the core. So we need to make a note of what is true and what is due to drilling. And then after we finish that, we bring the cores over to the second machine here. And this is called the Schmizzle. And what this does is it measures color in a very different way. So when I'm saying something is gray, it may actually not be gray. It might just be my eyes that are seeing gray. So this is this takes kind of a spectra of colors and creates a number which describes that color at every 2 centimeters, so then that they're comparable to other cores that have been imaged in the past. And we also measure magnetic susceptibility. So most sediment has some magnetic minerals within it. So this helps us see where those minerals are. For example, volcanic ash has a lot of magnetic minerals, so we can see spikes, which tells us that there's a volcanic deposit within that core. And then once we've described kind of the macro stuff that we can see, so the big changes that we can see, we come over here to our smear sliding section.
Smear sliding.
So this is smear sliding. So he just takes a toothpick amount of sediment and smears it literally on the glass slide.
Yeah, we dilute it with water, we cook it over there, and then we put some glue on, put the slide in there, and UV oven basically, and it dries out pretty fast. And then when this slide is ready, the microscope.
His hands are busy, so I'm going to leave him alone for a second. So again, we take a glass slide, we put sediment on it with a little bit of water, smear it out, and then dry it, and then put glue and a cover slip on top so we can keep that stuck there. So it looks like this up close. So you, again, like you barely can see it, but there's sediment on that. And it can look like that. And I'll let Lorna point out what she sees in our smear slide here.
Yeah, sure. So this is on one of the highest magnifications we've got. And what we can see here is these features here are actually microorganisms that live in the water column. So this one here is called planktic foraminifera, and this lives within the top 200 meters of the water column. And this one here is a benthic foraminifera, and this lives obviously on the seabed. And these are really great because they can tell us a lot about the paleo environment at the time. We can use them to look at oxygen and carbon isotopes, which can give us an idea of temperature. And we can also then look at diversity analysis to see kind of how the populations are faring as climate changes in the past. And then another feature we have here is this bit here, which is actually a volcanic glass. So we're finding a lot of them throughout our samples, and that is because we're in quite a volcanically active area. So when a volcano erupts, ash goes into the atmosphere and then falls down into the ocean, and this takes a very long time to settle onto the seabed and form sediment. So this is what we're seeing in our sediment.
Awesome. Thank you, Lorna. They're clapping for you. So that's our sedimentology corner. And this area is shared by both sedimentologists and hard rocks. So when there's sediment, This is all sedimentology world. When there's hard rock, it becomes a hard rock world. And let me just quickly go over to my hard rocks, because we haven't cored hard rock in this location, so I don't have any out to show you. But I do have some out from a previous location where they're doing the sampling party, where people can put stickers on what they want. So this is an example of what a hard rock core looks like. And so again, it's hard rock. This is actually mantle rock. So the scientists are very happy with what we were able to recover. And just to give you an idea, when we are coring, we have something called recovery. And it's just the percentage of core we received from drilling down 9.5 meters. How much of that 9.5 meters actually had rock in it or actually had sediment in it? So for example, this section is pretty empty until we get to this part of the core. So that means this section had low recovery, but this section's pretty full. So it had a higher recovery. And sometimes recovery is just dependent on the type of rock formation that we're drilling into, what drill bit we're using, the weather that we have. So there's a lot of factors our CM team, our drilling team, have to take into account when they're drilling. And they do a really good job to like counteract what they're encountering, but sometimes the rock formation is just tricky and it will just give us what we get. But we do get pretty good recovery. Like good recovery to me is like 50% for hard rock. Like that's nice. But sometimes if we get better, we're like jumping for joy. So that's hard rock. And our petrologists, our hard rock scientists, when they're done looking at it macroscopically, like what sedimentologists are doing here, like they look at it for the color, how many veins, what drilling disturbance exists, they'll take it also under the microscope. So they make something called a thin section. And a thin section is basically a slice of rock that's so thin, it's as thin as one of your hair strands. And which is crazy, right? Like you take a big rock and you make it as thin as my hair. But they are able to do that, and that's because when rocks, the minerals are that thin, they have a certain color they sort of show at a different light sources. And they can use that to understand what happened to the rock at a more microscopic level. What real stress did they encounter? And so, for example, I have over here our microscope area for our scientists. And Ravi's our micropaleontologist, which I'll come back to in a second. Tomo's our igneous petrologist, which means he looks at rocks that are born in magma. They haven't gone through change. And he is at our thin section area. So that's his, it's called a petrograph, right?
Yeah.
Petrograph microscope. So it has two different light sources that he can use to change. And then this is the image that he sees. But Tomo, I'll let you talk to us about thin sections.
So as you Tessa explained, so these are samples on the very thin slice of the rock samples we drilled into this area. And then that very thin slice allow the light to pass through it. So then we can see like minerals and we call textures through the microscope, using a microscope. And then this is a one way, and this is another way how to see minerals. You can see very colorful minerals. Yeah, these allow us to identify what type of minerals here and what kind of textures here. Yes.
Awesome.
Yeah.
And what do you use these thin sections for?
Because one of the big important question is this rock originally from a mantle, which is deeper part of the earth, but now tectonically exposed directly on ocean floor. So one of our main questions, why the originally deep mantle rock are exposed on the very shallow ocean floor, and these colorful minerals are minerals intact. It's very primary minerals in the mantle, but these gray minerals are hydrated from these primary minerals. So hydration means rock and water interactions. So the minerals contain the water in a crystal as a crystal structure. So it's solid, but the water content is more than 10%. It's surprising thing. So we understand how these rocks are formed and how what kind of histories are recorded in this rock, which allow us to understand, oh yes, Terranean Sea. So we know that the ocean is not always ocean. So the one of the questions, how Terranean Ocean was formed. So the question, to the hint for the understanding, we can get the information from this rock.
Awesome. Thank you, Tomo.
Yes.
So Tomo's on a team of five different petrologists. So he is an igneous petrologist. So again, looking at rocks when they are first sort of formed in magma. But we also have a metamorphic petrologist who specializes in hard rock that have already gone through changes and alterations. So they really work together. So when there's more of an igneous rock, Tomo might look at it more. And when there's a metamorphic rock, that's when Irini, or my metamorphic petrologist, will come in and take a look. So they really have their different expertise work together toward understanding what we're seeing in the rocks. And same thing with the sedimentologists. And then I have Ravi over here, who is my micropaleontologist, who's really key in a lot of what we're doing out here. So can you tell us, he's playing with some gloves.
Cool.
Tell us about what you're doing out here.
Sure. So Tessa might have talked a little bit about how the core comes up and what they do. So I'm one of the first guys to be getting the sediment sample for the core. So there's this part in the core which is called the core catcher, or the end of the core, and I get a small sediment sample from that section. And what I do first is bring the sediment sample here, and I do the dirty work first. So I wash the sample using this apparatus and using a 63 micron sieve. So what essentially happens is when I wash it, all the sediment particles which are smaller than 63 microns get washed away, and whatever the residue is, I collect the residue and put it in an oven for drying, and I later use that residue and pick out some species called planktic foraminifera, and I use these. So these species are called planktic foraminifera, and they look something like this. They're very beautiful microscopic organisms, and they are microscopic in nature. And what essentially my job is on the ship is to identify these organisms. These organisms were present during certain periods of time and have kept on evolving over the ages. So I identify this organism and recognize an age for when these species were deposited in the sediments, and as a result, I detect what the age of the sediment might be. So at this particular site, we are seeing sediments which were deposited around 5 million years. But there are some other expeditions where sediments as old as a few tens of million years to a few hundreds of million years were also recovered. As a matter of fact, as a part of this expedition, Paleozoic rocks or Paleozoic basement material was recovered, which is estimated to be around 250 million years old. So yeah, that's what I do on the show.
Thank you, Ravi. You're welcome. So when we drill into the earth, we are expecting to go back in time, but to make sure we actually are going back in time and to know when we go back in time, we have our micropaleontologist, Ravi, but we also have my paleomagnetist, Sean Yu, right here, that looks at the magnetic signatures of the rocks, because the magnetic signatures align with when the magnetic poles of north and south switch. And so he works with Ravi a lot to really just confirm. He's like, hey, I see 2 million years. And Ravi's like, I also see 2 million years. And then they can confirm each other. But if one says 2 million and another one says 5 million, they're like, okay, let's check. So there's a lot of validation that's happening on the ship.